So in this video, we're going to talk about how to solve exponential growth and decay problems. So remember, exponential growth and decay can be modeled using these formulas: y equals a times 1 plus r to the t for exponential growth, and y equals a times 1 minus r to the t for exponential decay. Remember that a is the initial. So we can also use exponential growth and decay formulas that involve e. So sometimes you'll see this in the formula. Remember that e is that special number, Euler's number. And it can be used in this formula, n equals n naught e to the kt, to model growth and decay. N naught is the initial amount, k is the growth or decay rate expressed as a decimal. And also, the way we represent growth or decay is that k will be positive if we have growth, and k will be negative for decay. T represents time. So it says the exponential decay model, n equals 12,000 e to the negative 0.03 t, represents the number of subscribers to a local weekly paper where t is the number of years after 1980 when the paper was first published and circulated. How many subscribers did the paper have in 2000? So we have exponential decay, and it gives us the model. Okay, I just want you to notice that since it's decay, notice that we have a negative in the exponent. And then it says t is the number of years after 1980, and then we know how many subscribers do they have in 2000. Okay, so let's write out this formula. We have n equals 12,000 e to the negative 0.03 t. So all we need to really know now is t, right, in order to figure out this formula. So it's t is the number of years since 1980. Okay, so what we're going to do is we're going to take 2000 and we're going to subtract 1980, because that's how we'll know how many years it's been since then. So 2000 minus 1980 is going to be 20. So we can just plug that in for t. So we have n equals 12,000 e to the negative 0.03 times 20. So that's going to be n equals 12,000, and then we have negative 0.03 times 20. And so that is going to be negative 0.6. And then now you can do this on your calculator. You can just do 12,000 and then times, and then we have to do e to the x, okay? The way you get e to the x is you're going to push second, and then you're going to push that ln key, okay? So you see there's an ln key right below the log key. It's 2 buttons up from the on button. So when you do that, it'll say e, and then it'll have a little exponent, and then in the exponent, you're going to type negative 0.6. Okay, so when we do that, we get 12,000 times, and then we do e to the negative 0.6, and then when you hit enter, it should give you the answer, which tells us that n equals 6,585.739633. So it doesn't tell us how to round in this problem, but we're just going to kind of use what it's telling us. It's talking about the number of subscribers. So since you can't have a fraction of a subscriber, we're just going to round that. So that's going to be 6,586 subscribers. Okay, since we're talking about people, we're just going to round to the nearest whole number. So in this problem, it says the exponential decay model, n equals 200 e to the negative 0.14 t, represents the number of people in a store t minutes after 12 p.m. when a super sale begins. How many people are in the store at 12 p.m.? So here's our formula, n equals 200 e to the negative 0.14 t. So what it says is that we have exponential decay, and it's t minutes after 12 p.m. Okay, well then it says how many are there at 12 p.m. So like notice 12 p.m. is kind of like the initial value in this problem, right? That's like our starting point. So remember that number that's in front of e, that n naught, is always going to tell us the starting value. So we can just look at the formula and say that it's 200 people. So if you don't believe what I did there and you want to actually plug it in, you would say that, well, t is going to be 0, right? Because it says t minutes after 12 p.m. Well, 12 p.m. is 0 minutes after 12 p.m., right? So you could just plug in 0 into this problem. So you get n equals 200 times e to the negative 0.14 times 0, which tells you n equals 200 times e to the 0. Remember, anything to the 0 power is 1. So that's how you get n equals 200 times 1, which still gives you the same answer, right? It's going to be 200 people at exactly 12 p.m. So now you can pause the video and try this example on your own. So it says the exponential growth model n equals 3000 e to the 0.02 t represents the population of Eulerville t years after 2010. What's the predicted population in 2050? So since it's the number of years after 2010, it's going to be 40 for t because that's how many years after 2010, 2050 will be. So when we plug it in, we get 3000 e to the 0.02 times 40. Then we can multiply 0.02 times 40, which gives us 0.8. And then if you do 3000 times e to the 0.8 on your calculator, you'll get 6,676.622785. Since once again, we're talking population, so we're talking about people. So we're going to round to the nearest whole number, which is 6,677. So we can also solve problems that involve continuously compound interest. So remember, when we have interest that's compounded continuously, we use the formula A equals PE to the RT, where P is the initial amount, R is the interest rate expressed as a decimal, and T represents time. So let's complete the table to show how an initial investment of $1,000 earning 5% interest compounded continuously increases over 50 years. So our formula is going to be A equals PE to the RT. And then remember that P is going to be the initial investment, right? So that's going to be that $1,000 that we have in our problem. And it says 5% interest compounded continuously. So that is going to be our R value. Okay, R is 5%, which if we move the decimal 2 places to the left, we get 0.05. Okay, so let's plug in these different values of T. Well, 0 years is just the initial value. So that is just going to be our original investment, which is $1,000. And then let's plug in 10 for T. So we get A equals 1,000 times e to the 0.05 times 10. Okay, so that's going to be 1,000 times e to the 0.5. And when we do that on our calculator, you should get, let's see, let's round to the dollars and cents. Okay, so that's going to be $1,648.72. So we can fill in our table. And now let's figure out the value at 20. So we once again have A equals 1,000, and it's going to be e to the 0.05 times 20. So when we do that, we get 1,000 e, and then 0.05 times 20 is 1. So that is going to be 1,000 times e to the 1, which gives us $2,718.28. And now let's figure out the value at 30. So we have 1,000 times e to the 0.05 times 30. So that's 1,000 e 0.05 times 30 is going to be 1.5. And when we type this in our calculator, we have 1,000 e to the 1.5. And that is going to be $4,481.69. And now let's figure out the value after 40 years. So we have 1,000 e to the 0.05 times 40. And so that's 1,000 e, and then let's do 0.05 times 40, which is 2. So 1,000 times e to the 2 is going to give us $7,389.06. And now let's do after 50 years. So we have 1,000 e to the 0.05 times 50. So that's going to be 1,000 e. And then 0.05 times 50 is going to be 2.5. So if we do this on our calculator, we have 1,000 and then e to the 2.5. And that will give you $12,182.49. So that's how you can use the formula to figure out the value of an investment after different amounts of time. So now you can pause the video and try this example on your own. It says, what is the final value of $4,000 invested for 5 years at 3.6% interest compounded continuously? And it says, round your answer to the nearest cent. So we're going to plug into the formula A equals PE to the RT. P is $4,000, our initial investment. 30.6% as a decimal is going to be 0.036, and then we have 5 years. So when we plug it on all in, we get 4,000 times e to the 0.036 times 5, which is 4,000 times e to the 0.18. And then when we round it to the nearest cent, we get 4,788 and 87 cents. So remember, exponential growth and decay can be modeled using y equals a plus or minus r to the t to make calculations involving real-life situations. When these situations involve interest that is compounded continuously, we can use a equals pe to the rt. And remember that the formula n equals n naught e to the kt may also be used to model exponential growth and decay.